Hello, I'm Dr. James Dborin. I'm the head of research at DoubleWord AI, and we're continuing our series of videos on advanced topics in LLM serving with today's video titled, What Should I Be Observing in My LLM Stack? So if we look at our mind map of advanced topics in LLM serving, we're going to be covering this section, observability, and it's going to touch on things like orchestration, and inference engines as well. So in today's video, we're going to be covering three sets of metrics or statistics that we think should be observed and monitored whenever doing self-hosted deployments of language models. And these three statistics, in the order that we're going to cover them, are the KV cache utilization. We're going to get into what the KV cache is and why this is a useful metric for measuring the total load on your system. We're going to look at the sequence lengths, both of incoming requests and model generations. And then finally, we're going to be looking at why we should be tracking user feedback. So let's jump in with the first one, KV cache utilization. So what do I mean by KV cache utilization? Well, first let's look at the KV cache. I do this in almost every single video, but the KV cache we're going to represent as a big square block of memory. So the KV cache is where the model stores its previously processed tokens so that it doesn't have to reprocess them in the future as it's generating. The KV cache is stored as a big block of memory stored on the GPU. And in this case, I'm going to divide it up into these boxes, and each box represents a token. So, for example, if I have two users currently interacting with my system, user 1 in orange might be using 7 tokens in my KV cache. Maybe they had a request with 4 tokens and the model has generated 3 tokens for them. And user 2 in green is maybe using 5 tokens. 2 tokens of prefill, 3 tokens of generation or something like that. And I can have many more users, many more colors. And each user takes up a slot in this KV cache. Now, not every request or every token has a unique slot in the KV cache. It's possible for tokens to share slots if they share a prefix, but we're not going to cover anything like that today. It won't be important, but no, there are sort of advanced topics in KV cache management that we're not going to discuss today. But the key point is that given a KV cache and the number of tokens it is being processed, I can calculate a KV cache utilization as the following formula. It's the number of tokens being processed. So in this case, we have 7 tokens being processed here and 5 here for a total of 12, divided by the total KV cache tokens. So in this case, it would be 12 divided by the number of boxes that are drawn here that I'm not going to count out. Now, why is this a useful metric for measuring the load, the total load in our system? Well, I'm going to answer that by first explaining why traditional metrics for measuring the load in your system are not useful. So some common metrics that people might track in a distributed cluster of some other type of computation to measure how heavily the system is being used include things like total number of requests, maybe something like CPU utilization, some measure of how busy the CPUs are, and then maybe even a metric like GPU utilization. If you're using GPU workloads. For example, this is the metric reported if you run the command NVIDIA SMI. So these are the things that people will usually use when they are trying to estimate how busy their system is. And it's useful to know how busy your system is because maybe you want to know if you've over-allocated resources. GPUs are obviously very expensive, and you want to know if you're getting the best possible use of them. You also want to know if actually your system is close to capacity, and if more downstream applications come online, it won't be able to support that load, in which case it's probably time to start looking at getting access to more GPUs. So it's really important to know how busy your system is, and typically people will look at some combination of these three metrics. And so we're going to go through these one at a time and discover why they're not so useful here. So the problem with the total number of requests is that in LLMs in particular, each request can have a very, very different computational budget. Some requests can be very, very cheap. For example, simple fact-based questions, the model will respond with a very short answer and the prompt is very short. And so it takes almost no time, very little processing is done in total, but sometimes the requests are very expensive. For example, if you have a RAG workload, you might have many thousands or tens of thousands of tokens in your context. If you're asking about long-form documents, contracts, regulations, books, and you're asking questions, the prompt can enter hundreds of thousands of tokens. That's very expensive, takes up a lot of space on the GPU, a lot of space in the KV cache. And if you're using the more modern breed of reasoning models, for example, the DeepSeek R1 model, then it's not just the prompt length you have to worry about, it's the thinking tokens. For particularly difficult questions, a request might take tens of thousands or hundreds of thousands of thinking tokens before responding with a short answer. Whereas another one might think for just a few tokens and then respond if it's a particularly easy question. And this is really hard to predict in advance, how long the thinking tokens are going to go on for. So if you track a metric like total number of requests, it's very possible that you see some sort of metric over time, like number of requests, and over time sort of steadily falling. You might think this is your system having a lot of slack in it, maybe you've over-provisioned your GPUs, but in fact what's happened is maybe your users have started switching to using a reasoning model such that they're able to send many fewer requests, but each request is taking up multiple times more tokens than it used to, in which case you're actually probably increasing the total load in the system, not decreasing it. So you want you want to find a metric that correlates with the amount of work that you're actually doing. One sensible option that is done a lot on normal CPU workloads is the CPU utilization. Now, the reason this doesn't work is that in GPU workloads, almost all of the work is being done on the GPU, not the CPU, and there's only occasional round trips to the CPU for it to issue another command that then gets run on the GPU. And if you're using something like CUDA graphs in your inference engine, which lets you request many operations and send them off in one go, and then they get run on the GPU, these round trips to the CPU can be very infrequent. And so a lot of the time, the CPU utilization is not a good metric. It's not very well correlated with the actual load on the GPUs. And so you'd think that one metric that is definitely well correlated with load on the GPUs is the GPU utilization. But unfortunately, this isn't the case either. The GPU utilization statistics that are quoted by a command like NVIDIA SMI are telling you how often something is being run on your GPU. Divides time into slices, and the percentage it reports is how many of those slices have some workload running in it, not really a good metric of how busy the actual GPU is, or like how much of its capacity you're using. So for example, if you're running a model with batch size 1, so a single user is using your model, this is likely to create a high GPU utilization. Like there's a lot of operations happening on your GPU, but you know that you can probably run with a batch size 100 if it's a small model on a big GPU or otherwise. And so really you have a utilization of the system of about 1%. But the GPU utilization reported could be very high. So in general, none of these are particularly useful metrics. A useful metric for measuring the load on your system is the one we discussed above, which is KV cache utilization. The thing that typically stops another request being able to be processed on a GPU, that will mean a user has to wait, or that will have to wait in a queue, is the fullness of the KV cache. If a KV cache has only 2,000 tokens left in it, because it's processing other requests, and a user requests 3,000 tokens, then it can't enter into the KV cache and it can't be processed until the space is freed up, until another request is finished and is evacuated from the KV cache. And so the metric that really indicates that your system is full is the KV cache utilization. So if you want to know whether there's slack in your system or whether your system is at capacity, the most useful thing to look at would be the KV cache utilization of every individual node. It's also useful to measure things like how effective your load balancer is, or which models are consistently being used more than others. And so if you have some way of recording the KV cache utilization of each individual model, of each individual model type, so for example, all of your copies of Llama A, B, and then of your system as a whole, that's probably the best way of assessing the capacity of your system and making decisions on GPU procurement or otherwise for your deployment. So moving on to the second metric that is worth tracking is statistics on sequence lengths. So, for example, it's probably useful to know things like the distribution of input sequence lengths for your users' requests, things like the distribution of output sequence lengths, size of images that they're sending, which creates a number of image tokens, things like that. So anything that sort of affects the number of tokens that goes through your system. I mean, this relates closely to what we just spoke about with the KV cache, seeing as the number of tokens and the system's capacity to manage tokens is a good metric of the busyness of the system, but there's other reasons why in particular you want to care about this. So, for example, one reason that you probably should care about this is that it ought to affect the configuration that you use to set up your cluster. There are various settings, configurations within inference engines that quite tightly control its performance under these settings. So if your users are passing in very long sequence lengths, if they're passing in very long sequence length inputs, then this is likely to impact some of the decisions that you're going to make when you're actually setting up your cluster. It might affect like your model choice. Maybe in order to have greater capacity in your system, you're going to pick a model that supports window detention patterns so that the long sequence lengths take up fewer tokens in your KV cache. Maybe you're going to choose a sort of Mamba or other linear attention model in order to get faster processing times for your long sequences. Maybe you'll pick a model or fine-tune a model yourself to have some sort of sparse attention pattern to make processing faster, or switch to using some sort of sequence parallel configuration for the model if you don't want to change the model, or you don't want to fine-tune it or change any of its parameters, in order to make this processing of long sequences faster, in order to give the downstream users a better experience. And similarly, if you sort of observe the opposite effect, maybe your users are using a lot of reasoning models and the number of output tokens is much higher than the average length of input tokens, maybe you can switch the settings such that it favors high-speed decoding instead of high-speed prefilling. So prefilling and decoding have very different computational profiles. Processing the prompt, the prefill stage, is compute bound, and the output in the actual tokens, the decode stage, is memory bound. So you don't particularly need to know what these terms mean, but the kind of decisions it might impact is if you wanted fast prefill time for longer sequence lengths, you might go with something like FP8, quantization, or something like that, something that decreases the model's, the amount of work that the model has to do. But if you're memory bound, so the decode is the largest bit of your workload, which is often true for these reasoning models that spend a long time decoding. You might choose like a weight-only quantization. For example, the quantization is provided in the GGUF model format or AWQ or GPTQ. These are particularly good at memory-bound decoding heavy workloads. You might also pick slightly different configurations of your tensor parallelism, and things like that would be different if you're prefilling or decoding. This is the big idea behind NVIDIA's Dynamo release, is that you can have different configurations for prefilling and decoding, but that's only really going to be useful if you already have an idea of what is the ratio of work done in the prefill to decode in your cluster based on your downstream applications. It's very easy to accidentally, in Dynamo, to accidentally provision too many prefill workers and too many decode workers, and too few decode workers, for example. But if you're in a very memory-bound, decode-heavy set of workloads, then you should probably be changing that up. And so this is a useful set of metrics to keep track of. The other thing is, if your users are sending in long prefills, but in particular if they have shared prefixes. So for example, this is common if your downstream application teams are using very long system prompts. Then such that a lot of these prefills are just repeating the same work over and over again, then it probably makes sense to look into some sort of inference optimization technique like prefix caching. And a good sign that you might need to look into whether this is the case is that there are lots of long prefills and people are waiting a long time for their first tokens. And if you determine that this is because of things like long system prompts, a technique that's available now in most inference engines like prefix caching would be very useful at speeding up the response times from your system and decreasing the overall load on the system. So all in all, it's a good idea to keep track of these sorts of statistics so that you can better configure your system, have the overall throughput be higher, so that you don't have to go and buy more GPUs before you absolutely have to. So finally, the final set of statistics we're going to look at isn't exactly like a cluster health statistic, but it's closely related to the performance of the model, and that's user feedback. So when you deploy a model, it's extremely valuable to collect some sort of set of downstream statistics, end user statistics on how good the model's performance is. So something like thumbs up or down, rating out of 5. So maybe generate 2 answers and say which do you prefer. I mean, for example, you might generate one from an 8 billion parameter model and a 70 billion parameter model and see which the user prefers. And the reason that you want to track this feedback is because it's probably the only actual good way of assessing the quality of your output, and it's also extremely useful at improving the model later in the future. So everyone always wants to know how good their deployments are, how good their applications are, and there's all sorts of tips and tricks around things like model drift and checking if the input distribution is sort of drifting over time for an AI model. And the problem is with LLMs, all that is so much harder to do because we're talking about drift in the space of all possible words and sentences and phrases and images, and it's essentially impossible to do. And so the best way to tell if your model is performing well at the start and if it's continuing to perform well is to collect these statistics from the downstream users, and calculate things like a rolling average of how likely your user is to thumbs up the response or continue to engage with the model and ask more questions versus like click off the page and leave it and go interact with another tool instead, or to copy the response indicating that they might be using it in some downstream purpose or something like that. Like you want some set of statistics that is telling you in the real world how useful these models are, and that's how you're going to be able to, for example, determine whether an 8 billion parameter model or a 70 billion parameter model is useful for your task. If you can deploy an 8 billion parameter model, you obviously should. This would be orders of magnitude cheaper and easier to do. But the question of do I know if it's good enough is almost impossible to answer without getting actual downstream users. You can do things like LLM as a judge, ask more powerful LLMs which answer they prefer. You can collect small gold standard data sets and compare their performance on that, but nothing really beats this downstream data collection. And so if you want to answer questions like, can I use an 8 billion param model? Can I use a quantized model? Or something like that. Anything like these questions which have really big impacts on the overall cost of the cluster to you, you can only really answer with these downstream statistics. And so it's important to track them and store them aggregated per sort of model type, and say, so you can answer a question like the windowed average for the quantized version of the 8 billion parameter model is a 43% like rate and a 57% dislike rate, or the win percentage of a 70 billion versus the 8 billion is 82%, or something like that. Those are the sorts of statistics that you really want to be able to answer in order to just be able to make decisions about what models you're hosting in your cluster and things like that. And there's another reason that you want this information, and that's for training models to improve their performance. So if I have like a big database of query, response, and some sort of rating, I have a query, I have a response, I like this one, I have this, I don't like this one. This is a really powerful resource for training the models. So if you take this data set and you just scrape out the positive ones and then you train a model on that data set of query response, we call this something like supervised fine-tuning. And this is a really good starting point of being able to deploy like smaller models. So maybe you start your deployment with a 70 billion parameter model, you collect a bunch of these positive query responses, and then you use that to train a smaller model like an 8 billion parameter model to decrease the cost of overall serving. And this is a good start for that. You can do even better if you have some of this preference data that I talked about before. For example, which do you prefer? So for example, if I have a data set that looks a bit like this. So I have one query, and then I have two responses, one from an 8 billion parameter model, one from a 70 billion parameter model. And I have information like it preferred this one, it didn't like this one. I can use this information now to construct a data set where I try to encourage answers like this and I discourage answers like this. And this method broadly is referred to as DPO, and it's a variant of fine-tuning that can make use of these preference examples to improve upon the supervised fine-tuning we talked about above and get a bit closer to the performance of reinforcement learning, which seems to be the sort of gold standard in improving models. This is somewhere in between. And then finally, I can do something like take this data set alongside other types of rewards, like verifiable rewards, rewarding for tool use or rewarding for correct answers in something like maths or whatever. I could take this and train a reward model which has a sort of understanding of what makes good responses and what makes bad responses, and then use reinforcement learning to improve the model's outputs against this reward model. So you can use a method like PPO or GRPO from the DeepSeek team and improve the model online against this reward model. And so this would be the sort of best way of really squeezing out all performance possible from a smaller model. But it's only possible if you've been collecting this user response data. And you can have other sorts of types of data in here as well if you're deploying agents which are interacting with other tools like databases or APIs that you have access to. Then you can measure percentage of successful uses of the APIs, successful calls to the database, and use those successful and unsuccessful calls to fine-tune them to make them better agents as well within this setting. So today we've looked at 3 different metrics that you should be logging in your self-hosted LLM inference server. We've looked at KV cache utilization, which is a gold standard metric for measuring the load on your system and whether you've over or undersized the compute resources in your system. We've looked at the sequence length statistics, which will tell you a lot about how you should be configuring this system for maximum performance to satisfy your downstream users who are interacting with it. And then finally, we've looked at user feedback, which you should be collecting as the only real way of knowing if your system or your models are still doing a good job over time and for improving them over time.